Test 1 2 3. All right, again, my name's EJ Daigle, Dean of Robotics and Manufacturing here at Dunwoody College. I'm going to do a little short lecture here on analog I/O as it pertains to the RS500 Allen Bradley Rockwell Software 500 programming environment. So the first thing I want to talk about is just some basics about what is analog. When we talk about analog I/O, everything we've done up until now has been digital, which means that when I turn this switch on, the light is either on or off. But what we know is when we get into the real world, we might have a tank, and the level of a tank can vary, from, let's say, 0% full up to 100% full, and it can go up and it can go down, or for that matter, the temperature of the tank could even change to where maybe the tank temperature could be 0 degrees C all the way up to 100 degrees C. A pressure vessel, the pressure in the vessel could change. The flow in a pipe could change. So the difference between analog and digital is that digital really has two states, 0 or 1. Analog has a varying state, kind of like the the volume knob on a stereo per se. We don't have the volume at 100% or 0%. We can adjust it to some value in between as to what we want. So analog inputs, they vary their resistance, causing a voltage drop that's proportional to the measured value. This can then be measured using a PLC analog input. Again, our examples, things like thermistors. The word thermistor means, we're combining two words, thermal with ister, which means like a thermal resistor, which means that it's a resistor that changes its resistance with temperature. Or a flow meter. Flow meter might, at 0 gallons per minute might give me a 0 volt signal, and 100 gallons per minute might give me a 10 volt signal. And it would be nice if it was always that easy, if these things were perfectly linear. Unfortunately, they're not. But for today's lecture, we'll try to keep it simple. A pressure transducer. A pressure transducer might have a current or voltage output that is proportional to the pressure measured. In some cases, transducers will output a digital signal as well. So there's all kinds of things that we can do. Temperature sensors, various temperature sensors, relative humidity probes, all of these things. But the idea being is, let's say I have a 10 volt source, and I go through this device that's going to vary its resistance. I'm going to call this like a thermistor, and that thermistor then goes to my PLC analog input. So I'll call this AI for analog input, and that analog input has some internal resistance that then goes back to ground and connects to the same ground, as your 10 volt source, let's say, right? So your 10 volt source also has a ground over here. So what happens is, as this resistance changes, the voltage felt by the PLC will change, and we can make that 0 to 10 volt signal. We can turn that into a digital value. So really, an analog input really is an A to D converter. What we're talking about is the conversion of an analog voltage or current to a digital numerical number of some sort. All right, so the SLC 500 analog module, this is the one that we're going to be using in the lab. It's a 1746 NIO4V. So this will have both analog inputs and analog outputs. So we've got a couple different options. One of the things I want to note as we look at the module here, you guys can look up the specs as part of your pre-job and so forth, but we're probably not going to pull the module out. So I want to show you this thing on the side of the module here. You'll see this current selection or voltage selection. And typically when we're talking about voltage, a lot of times we'll talk about 0 to 10 volts DC. We might talk about negative 10 to positive 10 volts DC. And we're talking about current, a lot of times we're talking about 4 to 20 milliamps. So depending on the sensor that you're working with, if you're working with a transducer, or you're working with a thermistor, or you're working with a flow meter, you can get them with different outputs. Of course, you can get them with digital outputs as well, but if the output's 0 to 10 volts, then I want to make sure whatever channel I'm on, if I'm working with voltage like this one right here, then I would want to make sure that my module is set up for voltage. So I'd want to make sure my dip switch is turned off. So there's some dip switches down here that correspond to this channel 0 and channel 1. So I would want to make sure that the dip switch for dip switch 1, which would be channel 0, I want to make sure that that guy is turned off. And if I want that voltage for channel 2 as well, I'd want to make sure that dip switch is off. So it gives you an idea of what we're looking to do to set up our module to measure voltage or current. And in our lab, everything's going to be voltage. But again, out in the industry, we may be dealing with current sensors as well. So analog inputs. What do analog inputs do? Well, the PLC converts the analog voltage or current, okay, we're going to deal with voltage, into a 16-bit word that we call a digital value. You access these values by using the module location and the word address. So up until now, most of what we've done has been what we call bit addressing. So if I have an input in slot 1, I might get I:1/0, or I might get I:1/1. That's how we would address a bit. When we start addressing a word, you'll notice it looks very similar, but now instead of the slash, it's I:3.0. And what that means is input. It's an input. In this case, it's an analog module, so it's an analog input. That analog input module is in slot 3. The dot signifies that we're dealing with a word. So slot 3, word 0. So we're not going to just get a 0 or 1 stored in that location. It's going to be a 16-bit word. And that 16-bit word, if we recall, if you take 2 to the 16, that equals 65,535. And for our sake, that means we can have an analog integer that goes from negative 32,768 all the way up to positive 32,767. So that would be our signed version of this 2 to the 16. Analog outputs. So where an analog input takes a voltage and converts it to a word, and oh, by the way, on analog input side, we call these read-only, which isn't to say that we can't, change them. It just means that we're reading the digital value. We're not writing it. On the analog output side, what we're doing is the PLC is taking a digital value that we send it and sending it out as a voltage. So analog outputs feed analog devices that vary mechanical or electrical signals proportional to a voltage signal. So the input, the analog in, so if I write up here AI, the analog in was an A to D conversion, was an analog to digital conversion. The analog output is a D to A conversion. So now we tell the output, hey, I want this digital value, 16,000. It's going to convert it to a voltage and send that voltage out on the screw terminal. And examples of this would include things like proportional control valves, speed controllers, three-way mixing valves, VFD speed inputs, so on and so forth. One of my favorite ones to look at is what I would call a three-way mixing valve. You have, let's say, hot water coming in on one pipe. You've got cold water coming in on another pipe. And what you do in the middle here is you have this three-way mixing valve. And this three-way mixing valve can have a little gate in it that can go maybe between 0 and 100. And then it's going to output a certain temperature. So the cold water comes in here, the hot water comes in here. And right now you can see I've got my gate all the way to one side. So I'm going to get very little hot and a lot of cold. But if I move that gate over to where it's over here, now it's going to be closer to 50-50 on that. And I get a mix over here. So I could tell it what position to go. It's kind of like your shower at home. You have one knob for your shower. Then what you're doing is you're moving that knob back and forth to determine how much hot and how much cold to mix together. Just a good example of a device that we might use an analog output with. And I say I want 50%, it puts it here. I want 0%, it puts it over here, and I want 100%, it puts it over here. So I get either 50% hot and cold, or I get 0% hot or 100% hot, depending on where that little gate, whether it goes this way or it goes this way to let hot and cold water in. So the analog output converts a word length 16-bit digital value. So again, this is a D to A conversion, okay, into a current or voltage proportional to that digital value. You access these values using the module location and the word address. So now, same thing as what we just did, but now we're talking about an output. So again, we've got an analog module in slot 3, and we're going to address it as a word as signified by this dot. So slot 3, word 0 is what we're going to use to address that analog output. All right, now this is where it gets a little bit interesting. This is where we want to know, how does this thing work? Well, the way it works is you can see here, we'll just think of it right now from an input standpoint, and it's the same for an output. But let's say that we're getting a voltage, right? We've got a 10 volt signal here, and that's going through some varying resistance here that's going to feed my analog in. So I'll call this my analog input screw terminal. And if that analog input screw terminal, for whatever reason, reads 0 volts, then the analog word is 0, 0, 0, 0. I'm going to draw it as 5 zeros there. All right. If that resistance goes way down to nothing, right, then I'm going to get all 10 volts over here. If I read 10 volts, then I read 32,767. Now, this is where some people sometimes get a little messed up and say, well, what if it reads, what if my analog word is 11,110? What does that mean? Well, we do the same thing here. We've got our values here. We know these two values, right? So I can say, well, let's say 11,110 is to 32,767. I set that equal to, that should be a 7, 32,767. I set that equal to some unknown value is to 10 volts, which is to say that 32,767 equates to 10 volts. 11,110 equates to what? I just do my real quick cross multiplication here. So I get 32,767x equals 11,000, let's see, 111,100, because I multiplied that by 10. So now I'm going to jump into my calculator here. I'll keep my annotations here and just open up my calculator real quick. And I got my scientific calculator. So now I'm going to take that number that I just calculated, 111,100. I'm going to divide that by 32,767. And I'm going to get a number like 3.39 volts. So I would expect that if the analog word was 11,110, the voltage would be I'm going to make it 3.4 volts DC. I'm going to round them all to one decimal place. And we think, well, does that make sense? Well, if at 10 volts it was 32,767, and if 11,000 is pretty close to a third of 32,000, well, then 3.4 is pretty close to a third of 10. So we figure we got the right number there. That looks pretty good. Let me see if I can. There we go. I'm just going to take my, put an eraser on here real quick. All right. Oh, maybe I'm not going to put an eraser on here. Let's try this. Let's just click out of these here. Let's get rid of our values there. So that was Control Z real quick. That was a 3.4 volts, I think is what it was. Yeah, that's what it was. So that first one was the 3.4 volts. And so boom, 3.4 volts DC. Now the next one here is 6.9. So let's do that 6.9. 6.9 is to 10 as some value is to 32,767. Now I hope that doesn't screw anybody up. I actually flip-flop these, right? But it's the same thing. It's 10x equals, and I'll need my calculator this time. Keep my annotations here. Go back into my calculator. We go 32,767 multiplied by 6.9. I get that number, and I divide that by 10, and I get 22,609. So let's put that guy on here, 22,609. The reason why I like these numbers is they kind of make sense here, right? So 6.9 is about 2/3 of 10 volts, isn't it? So it would make sense if the full range was 32,000, I might expect about 2/3 of that for 6.9 volts. That makes perfect sense. Let's get rid of those and let's just try this next one here. Our word is 314. So I don't know what the voltage is. The voltage is to 10 as 314 is to 32,767. And again, if you don't know what I'm doing here, it's just a quick cross multiplication. All right, so I get, let's see, it's 32,767x equals 3,140. And I just got to divide that out. And I'll keep my annotations here again. And we'll go back into the calculator here. 3,140 divided by 32,767. I get 0.095 volts. Let's try that one more time. 32,767, or excuse me, 3,140 divided by 32,767. 0.095 or 0.096 volts. So that's a very small number. Well, guess what? That's probably, and I'm working off of this, so I'm going to go 0.1 volts DC. 0.096 or whatever, 0.1 volts DC. Well, that makes sense, right? This is extremely, extremely small, right? 3,200 would be 1 volt, right? So 320 would be 0.1 volts. So that's probably a good number, that 0.096 or whatever it was. 9.6 volts down here, we can take 9.6 is to 10 as some number is to 32,767. So I get 10x equals those two multiplied. Let me do that real quick. I'll keep my annotations here. So I need 9.6 times 32,767 equals that. And I need to divide that by, I think it was just a 10, right? Yep, divide that by 10. 31,456. Now, one of the things I want you to note as I write these, that thing had a decimal point to it. 31,000, I think it was 456 if I remember. I hope that's what it was. I'll test it one more time just to make sure I didn't screw up that number there. Calendar, yeah, there we go. I forgot my numbers already there. Okay, 9.6 times 32,767 equals that, divided by 10, 31,456. Now what I wanted to note here though is you'll notice that this guy actually has a decimal point to it, right? However, remember what we talked about when we talked about this analog input or this analog word. This analog word is a 16-bit, be careful here, it's an integer. Depending on the PLC that you're working with, you may truncate that decimal or you may round that decimal. It doesn't really matter too much because we're talking about, point something of 32,767. So your resolution is fairly large. But we do not want to have a decimal point. So if you put a point number over here, you're actually incorrect. It's fine to have a point number on the voltage side. It's not fine to have it on the word side because that's an integer. Remember that. This guy over here, these are all integers, so they have to be whole numbers. In the case of the Allen Bradley software, this is typically going to round the decimal. But again, there are other PLCs out there where it will truncate the decimal, which means it'll just chop it off and just make it an integer. So let's talk about an application real quick. I'm going to go to the DigiKey website. I'm going to grab this part number here real quick. I'm going to discard my ink annotations this time because I don't need them. And I'm going to just grab this part number here and go to DigiKey. If you haven't done this, DigiKey is an outstanding website for researching electronic parts. I hope this one is in here, and I think it is. So this, yeah, there we go. So this tells me here's a product overview. It's got some sort of temperature probe here, temperature sensor, negative temperature coefficient, it says. Here's some data sheets on it. If I want to look at the data sheet on this thing, it'll actually tell me all the information on it. So positive and negative temperature coefficients. The accuracy is 0.2 degrees C from 0 to 70 degrees C. Basically, this thing is designed to be hooked up to a cable and can either be placed into a tank, or you can see this one's actually got a threaded nut. You can be threaded into a tank. But the idea is you could take a measurement of a fluid, or you could take a measurement of of a pressure vessel or something like that and measure the temperature that's internal to it. So kind of a cool thing to see. And in this case, we know it's a 10 k ohm negative temperature coefficient probe. And so we're just going to pretend here, we're not actually doing this in real life, but we'll pretend at this point that what we did was we took this probe, this thermistor, and we dipped the thermistor in ice water. And what do we expect about ice water? Well, at ice water, we'd expect, ice would be about 0 degrees C, right? Or 32 degrees Fahrenheit, either way, depending on how you want to, what system you want to work in there. And then we dip the same thermistor in boiling water right here, and we'd expect boiling would give us 100 C or 212 Fahrenheit, right? So we can see what we'd expect there. But also notice what we did when we did that. We also measured the voltage. So we're going to measure the voltage at our analog input. Now we're going to make an assumption which is incorrect. But there are sensors out there that are linear. Then there are sensors out there that are going to be more like an exponential or a logarithmic curve. So a little bit more math would be involved. But for the first time through, we're going to keep this simple. We're going to assume that our device is linear. What that means is that each 0.1 volt corresponds to some value in temperature change, and that same amount of voltage change is the same amount of temperature change as you move up. And what we want to do is we want to write a PLC program that will display the actual temperature based on those measured values. So the first thing I do, that was step one. I just want to figure out, I kind of want to calibrate my sensor. In ice water, I measure this, and in boiling water, I measure this. So I can see what my two values are. Now, because we've assumed it's linear, we're going to go to step two. And what I'm going to do is I'm going to create a little thermistor graph is what I'm going to do. So I can see that at 32 degrees, I read 3.4 volts. And at 212 degrees Fahrenheit, I read my 7.9 volts. Now, the other thing I wanted to do real quick was I wanted to determine what those word values were. So again, if you're not sure how to get that word value, well, we say this. We say 3.4 is to 10 as some value is to 32,767. You do your cross multiplication here. You get 3.4 times this and set that equal to 10x. And if you divide that out, you'll get the 11,140.78. You do the same thing up here for the analog word high value. 7.9 is to 10 as some number is to 32,767. You multiply 7.9 times 32,767, set that equal to 10x, and then divide it out, and you get your 25,885.93. Now we want to be careful here, right? Because what did we say earlier? We don't include these decimal places, right? So these should be integers. So 11,140. I'm going to truncate them this time, but sometimes I'll round them, sometimes I'll truncate them. Depends on the software I'm working with. But I'm going to eliminate those decimal places. So I've got 25,885. I've got 11,140.78. And I guess actually in this particular example, I didn't truncate the decimals, which is fine. It's not going to hurt anything. But now that I've determined that thermistor graph, and I've determined kind of what is my minimum word for my minimum temperature, right? So 11,140.78 goes with my minimum temperature, and my maximum word goes with my maximum temperature, which is my 212 here. That's my max. Now what I can do is I can come in here and I can actually bring in that analog input. So what I do is you'll see on this subtract block, what I've done is I've taken in I 3.0. So I colon 3.0. So this is my word value. This is my analog input. And remember what we said about this analog input is that analog input is going to be a number between 11,140 and 25,885. So I'm going to take that value, whatever that number is, and ignore this right now. I'm not actually looking at a real number, and you can ignore this one as well. But I'm going to take that number in, whatever it is, and I'm going to subtract this number here. So if my number is 11,140.78 minus this, then I'm going to get 0. Okay. And if my number is whatever the other one was, let's look at the max, was 25,885.93. So the max would have been 25,885.93. And the min would have been 11,140.78. Those were my max and min. So I'm going to subtract out the min and see how much above that I am. Okay. Now you'll notice this guy here, this number here where you say 14,745. Oh, what is that? 14,745. Well, if you look at that, what that is that's the difference between these two. So the range I have between these two is 14,745.15. That's the range between these two numbers. So that's kind of like my maximum scale between freezing and boiling water. It's a range of 14,745. So what I've done here is this tells me how much above minimum am I. So remember what's happening is the PLC is reading a voltage on that screw terminal. It's converting that voltage that it reads in I 3.0, I colon 3.0 to an analog value. And it's going to be an analog value in this range. So if it's 15,000, then I'm going to take 15,000, subtract this, store that in this integer file, N71. Okay. Then I'm going to take that N71 and ignore this one for a second. I'm going to divide that by the maximum range. So I want to figure out where am I at in the range. And then you'll see what I did here was I then took that percentage of the full scale range, multiplied by 180, and added 32. And so let's think about what that means here for a second. Let's try it with a value here. Okay, I'm going to see if I can delete these numbers here. I got to remember that. Okay, that's okay. Discard. Go back in. So now let's say that we get our first number in, and I would like to change my color if I can. Let's see if I can do that. Pointer options, color. I'm going to go to blue. This is kind of bright blue here. So let's say my number coming into I3.0, we're going to ignore this one and this one and this one for now, okay? Let's say my number coming into I3.0 right now is 11,140.78. Well, then that's what's coming in right there into I:3.0. That's what I'm measuring. So what I've measured is I've measured a voltage, and that voltage was, remember what it was 3.4 volts, right? And the analog module converted that analog voltage to the digital value of 11,140.78. Again, I don't like this because we're not using an integer, but that's fine. I subtract 11,140.78. I subtract 11,140.78 from that. What's going to store in N7.1 then, N7:1, is going to be 0. So this is what was in I:3.0, and that's what gets stored in N7.1. So I:3.0 is that. This is what gets stored in N7.1. Now N7.1 is right here, right? And so now what I'm going to do is I'm going to say, well, you know, I had my minimum value and my maximum value. This is the range between min. So min was 11,140.78. Max was, oh crap, I got to go back and look, 25,885.93. So it was 25, oops, sorry about that, 25,885.93. That was my max. And then the range between those two was 14,745.15. That's the range kind of between them. I'll just kind of put a range notation there. And so now what I do is I take this number 0 and I multiply it by 14,745.15. And I'm going to store that in F8 here. See that? So now F8:0 is going to get the number, what was it, 0 times that range. I get a number of 0 again, right? And now I'm going to come down here. And in N7.0, apparently we're going to store whatever this compute instruction does. So in this case, what was in F8.0 was a 0. We're going to take 0 times 180 plus 32. So 0 times 180 is 0, plus 32 is 32. The value that's going to get stored in N7.0, which is my temperature, is 0. And I'll call that 0 degrees C. Now you might be like, oh, that's pretty cool. That looks like it works. So let's try this then. Let's go and create one with our maximum value. So we'll take a red value here now. And now we know our max was 25,885.93. That's what's going to go into I:3:0. Then I subtract that from, I subtract 11,140.78 from that value. It's no surprise I'm going to get the number 14,745.15. That's what's going to get stored in N7.1. Now down here, I'm going to divide 14,745.15 by 14,745.15. The value I'm going to get out is 1.0. Then we'll store in float 8. And then down here, float 8 says, okay, I'd say, well, N7.0 is going to get float 8, which is 1 times 180, which is 180, plus 32 is 212 degrees. And this should have been Fahrenheit over here as well. Sorry about that. Let's pointer option. I'm going to try my eraser here. There we go. And pointer, color. Just trying to figure out my fancy. So that should be Fahrenheit. Still didn't pick the right color, but that's fine. So now let's pick one that's maybe not so trivial, because what we've determined now is we said, well, this works pretty good. But of course, we're doing things that we already knew, right? But let's pick one that maybe is a little more interesting. I'm going to do purple here, which maybe is kind of like a combination between red and blue. So it's not all hot, it's not all cold now. I'm going to pick a random number here, like 18,000. Okay, 18,000 is 7,000 above that and about 7,000 below that. So I would guess this is somewhere in the middle. I'm not sure. So now I've got to do 18,000 minus 11,140.78. I'll keep my annotations here. I'm going to have to go to my calculator here. So 18,000 minus 11,140.78. 6859.22. 6859.22. So let me write that over here. 6859.22. Got the wrong color again. 6859.22. So 6859.22. That's what's getting stored in N71. Now I'm going to take that 6859.22 and divide it by 14,745. So let's go back into my calculator again. So we'll take that and we'll divide that by 14,745.15. I get 0.465. That looks pretty good. So again, I need to change my color. 0.465, I believe, is what the number that we just got. So 0.465. Now, if you're wondering what that means, well, what it really means is this one was at 0% of the full scale. This one was at 100% of the full scale. This one's at 46.5% of the full scale. So now it's just a matter of doing the math down on the bottom one here, which basically says I want to take 0.465, I want to multiply it by 180, and I want to add 32 to it. And I get 115.7 degrees. So now down here, get my color back here. 115.7 degrees, I think, is the number. Notice we're storing this in an integer, though. So I'm going to say it's 115. I'll just call it 115 degrees Fahrenheit, so it's an integer. So you can actually see we're able to calculate the temperature for any value that came in between 11,140 and 25,885. Now note, it's kind of a poor example, right? The reason why this is going to be a little bit of a poor example is because we made an assumption which is just not true at all. Is we assume the sensor is linear. Okay. Now for the thermistor we were looking at, that's not true. The sensor would not be linear. I could drill deeper into the data sheet and find out exactly the function that defines the performance of that sensor. However, there are sensors out there that are linear, but for the purpose of this model, I really wanted to try to keep it as easy as possible for your sake here. Now you might say, wow, you know, this looks like a mess. I got to do this subtract, I got to do this divide, and I got to do this multiplication by. So basically here, how much above the minimum am I? Where am I at in the full range? And then multiply it by my new range. So I have to multiply it by my new range, which 180 is the difference between 32 and 212. And then my minimum is 32, so I have to offset it by 32. So I have to add that 32 in to get to the new range. You might say, oh, that's painful. Well, that's a little bit painful. You can find in RS500, they've got this nice called scale with parameters function, and it does it all for you. So imagine, take all that stuff that we just did, build it into one box. So now all you do is you say, okay, input 30, that's where I'm going to get my analog input. Ignore this value, ignore these values here. Okay. My input minimum, okay, we said our minimum was 11,140.78. Our max was that. Well, that's based upon us putting this thing in ice water and putting it in boiling water, right? So I put in my input minimum. I put in my input maximum, as I would expect. And then I'm going to put in my scaled minimum. What do I want my new range to be? So if this is my existing range I get from boiling and hot water, or excuse me, from ice water and boiling water, this is what I want to scale it to, 32 to 212, and I want to store it in here. So this is my scaled min, my scaled max, and then my new output range. And so you can see how this would be, the scale with parameters is much simpler and easier to use than what we had previously tried to do. So it's going to be a lot simpler to look at on this one. All right. And so then step 4, so we've gone through, step 3 the hard way, step 3 the easy way. Step 4 would be then, okay, now I've got this HMI that I want to display some values for, right? So I want to say, okay, well, create a PLC program that converts the analog values as necessary to display the data on the HMI. Illuminate an LED as appropriate for the following temperatures. So what I can see right now is if I use this scale with parameters, or for that matter, if I take this value here and I now have a value in N70 that's going to go between 32 and 212, right? And I should have been careful here. I got something wrong right here too. This should have been 32, right? Because it was, note here, it was 0 times 180 is 0 plus 32. So I didn't do my offset there. So I just caught that mistake there for you. Now, we know that this value that's going into N7 is going to be between 0 and between 32 and 212. So now what I would do is I might say, okay, I've got everything I need here. Well, what I'm going to do is I'm going to say, look, if the value is between 32 and 65, so I might do, is my value in N70, is it greater than 32? Oops. So is it greater than 32? I hate making that mess there. Let me fix that real quick here. Go back to my eraser. There we go. Pointer. Go back to my color. All right. So is N70 greater than 32? I don't need that decimal there because it's an integer, N70. And, so I put another one in series. And is N70 less than, let's look at what our value was, 65. I want to get rid of that decimal so you're not dinging me on that. So is it greater than 32 and is it less than 65? Then I'm going to go ahead and energize B3:0/0. Now, if you don't remember what that is, that's a binary file. No different than an output bit. It's just a virtual file. We're not actually eating up a screw terminal with it. So that's going to give me the red light. And then the green light will be between 65 and 75. So I'll do the same thing here. I'll do a greater than. Is N70 greater than 65? Is it, oops, sorry about that. And is it less than, is N70 less than 75? Well, maybe then I'll go to a B3:0/1. And then the last one down here would be one more, just like we've been doing. So I need a greater than, I need a less than. Running out of room down here, sorry about that. And that's going to go to a B3:0/2. And that one will be 75 to 212. So is it greater than, is N70 greater than 75, and is it less than 212? Now I would recommend this less than 75 and greater than 75, I would probably recommend making this a GEQ, a greater than or equal to, and this one being a less than. So if it was 75 exactly, you would never wind up with a spot where you don't have any lights on. But what we know now is we know that the red is this one will be red, this one will be green, and that one will be red. So I guess what we're saying here is with red, green, and red, we're saying, okay, as long as it's between 65 and 75, our temperature is good. If it goes below 65 or it goes above 75, maybe that's an alarm condition. Now you might say, okay, well, what are we going to do with that? Because we need to do something with the HMI now, right? So then what I would do is I would create an HMI screen like this. And on that HMI screen, I might want the actual temperature, you know, where I would have a numeric display like this, boom, 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 a numeric indicator, and I would tag that numeric indicator to N70 so I could look at the actual temperature. But in addition to that, I would have a red lamp that I would tag to B3:0/0, and maybe I would call that the low lamp. I'd have another red lamp that I would tag to B3:0/2. Maybe I would call that the high lamp. So I've got a high or a low condition. And then, lastly, I would have a green lamp right in the middle here that I would tag to B3:0/1. And maybe I would call this my normal setting. So you can see how really simple, by wiring up our analog input to a thermistor and wiring it up to the screw terminal associated with I:3.0 by using scale with parameters. So I can get my value out from 32 to 212 right here. That's going to be my scaled value. And then by using some simple compare instructions and having those compare instructions turn on these different binary files. And oh, by the way, I've also stored the temperature in N70, right? I can display the temperature here, and I can also have a red, green, or red light to tell me if I'm in an alarm condition or if I'm in a normal condition for the temperature value I'm concerned about. With that concludes the analog I/O section, and although we only looked at it from the analog input section, we can do the same thing from the analog output section. So instead of reading to I:3.0, instead of reading that into my scale with parameters, I could always do some calculations internal to the PLC, and I could write a value to O:3.0. So I could move a value into it. So like, as an example, if I determined my temperature was, where am I at here? If I determined my temperature was too low, like right here, I could say, oh, well, instead of applying 5,000 analog word to the heaters, I want to double that. I want to apply 10,000 analog words. So I'm going to start heating the heaters up so I can move a value of 10,000 in. And I could do that proportional, and that we won't get into that yet, but we could do a proportional gain, or we could do a PI gain, or PD gain, or PID gain to actually determine how we want to scale that heater on and off. We call those proportional controllers is what we call them. But anyways, we'll get to that in a different topic. So thank you for your time.